Okay, so here we go. Last time we just kind of barely talked about this stuff here. This is a little bit of a stretch of propriety for Math 219 anyway, so I don't want to spend too much time on this. But I just wanted to let y'all know that there is kind of a continuum between the two extremes of examples of physical examples of divergence and interpreting divergence that we saw previously. So we saw this light bulb example where fluid is being generated, but the density is constant, right? And then the other extreme being this, what I'm calling evacuation of a gas, where it's exact opposite, that no fluid's being created. There is no fluid generation. It's all a matter of density changing, right? So, in between those extremes, what we have is this equation right here is a simple way to sort of recognize that both of those features could be happening at the same time. They're not mutually exclusive, right? So anyway, for whatever reason, if you have a fluid that is being generated to any extent, right? And by the way, positive or negative, maybe the fluid is disappearing, maybe it's being destroyed somehow, whatever, right? Whatever that generation rate is. When you generate fluid, there's really only two things that can happen. One thing that could happen is that fluid could leave your region, in which case, if it does, it's contributing to flux. Right? Now, the other thing that could happen is the fluid could not leave your region, in which case, it's contributing to a rate of change of the total amount of fluid in your region. Right? And so this is an easy way to motivate, I think, this equation here that shows the relationship between fluid generation rate, the rate of change of the quantity of fluid, and flux. Right? So, in the first example that we saw, fluid was being generated, but there was no change, there was no sort of collecting of the fluid inside. And so all that was, in our first example, was this term was zero. And so flux tells me about how fast the photons are being generated, namely how bright's your light bulb. So that makes sense. And then in the other example, no fluid was being generated. Right? And so flux meant that the rate of change of quantity of fluid was decreasing. And that decreasing is the minus sign that you get when, of course, you move this term to the other side of the equation. Anyway, that's just a way to kind of unify those two examples. Of course, you can divide by dV, as it were, and of course, flux per unit volume is divergence. Mass per unit volume is density. And okay, now we have to kind of, I have to make up a new concept here. This generation rate is not something that we've talked about before, but I'm generalizing that as generation rate density. How much fluid per unit time per unit volume inside of your region. This is a little bit of a new concept to kind of wrap your brain around. But anyway, the point is, in general, this is an interpretation of divergence applicable to any example that has any combination of the features of those two previous examples. Okay, all right, that's enough. Okay, so let's talk about gravitational fields. A lot of y'all have seen gravitational fields before. We've previously discussed how they're inverse square radial, right? And that's what this formula right here is. Don't forget, you need, in some sense, one of these three factors in the denominator goes to making your direction a unit vector direction, thus making the remaining inverse square. Right? Okay, so we talked about that a long time ago. Real quick, this is for a point mass. If you have a single point mass, which of course is not a physically real thing, right? But this is a fantastic approximation for actually real things, which is very, very small little pieces of mass. Okay, so here's the radical shift in point of view that I want to offer. And we didn't say this at all when we previously saw this inverse square radial gravitational field for a point mass. We did not say the following at all, and that is, it's got the same structurally the exact same vector field as the flow field, the particle flow field from a light source. This is basically the exact same vector field as if you were to write down the light bulb photon flow field from the previous page. It's inverse square radial also. So that's weird, right? I mean, what are the odds? You have two totally different phenomena. Light and gravity. And they have exactly the same vector fields describing them. What are the odds? Right? So this is an eyebrow raiser, and it makes some physicists think, maybe this is a sign. Maybe the fact that the vector fields they're exactly the same. That's so weird. Maybe that's what gravity is. Maybe gravity is communicated the same way light is. We've kind of all accepted the idea that light is communicated by tiny little particles called photons. Maybe gravity is communicated by tiny little particles called gravitons. So now, whether this is true or not that's a matter for the physicists, and it's a very deep and unapproachable question, right? As to whether this is physically real. I have no interest in the matter of whether this is physically real. My point, because this is not a physics class, right? My point here is that you can pretend that gravity is literally communicated by little emitted particles in the same way that light is communicated by little bitty emitted particles. And if you do pretend that that's what gravity is, that's how gravity works, it's going to never lead you astray. Because that's literally exactly the vector field that gravity is, it actually is in the physical world. So I think that's a great idea. Let's think of gravity as literally being communicated by little particles. I think this is a very useful concept. Okay, so with that in mind, here's a picture then of the gravitational field. Notice it looks exactly like the picture we drew for the photon flow field from a light bulb, where this was the light source, right? The source of photons. Now it's a piece of mass, and it's the source of gravitons. Okay. Alrighty. So here is a calculation we can do. Temporarily ignore this negative 4 pi g. We'll come to this in a second. I'm going to put a question mark over that. But let's focus our attention just on the remainder. I mean, it's a common factor, right? Who cares? So mass, triple integral of density dV. The purple part there is old news, right? That's, kind of the definition of density in some sense, right? Mass is triple integral of density. No surprise there. Okay, now what's with the 4 pi g? Negative 4 pi g. That negative 4 pi g we put in there so that this will work. There is a relationship between the mass inside of a surface. We've got a spherical surface there, not that it matters. But there's a relationship between the mass inside of a surface and the amount of flux of the gravitational field that you will measure on that surface. You might say through that surface. Namely, how many gravitons are flowing through that surface per unit time. Right? And to find the relationship here between mass and flux, it's really not that big of a deal. If you know the mass, you can plug into here and see exactly what your gravitational field is. And once you know your gravitational field, you can just directly brute force compute the flux through, let's say, a sphere. Right? And when you do all that, I don't want to get bogged down in the details. This is not a physics class. But when you do that, what you find is that the relationship between these is this proportionality constant of negative 4 pi g. And that's why I multiply the top equation by that negative 4 pi g so that I can then write this down over here. All right. Now, what else can I say about flux? We've talked about this equation. We've talked about this equation. Now, what else can I say about flux? Well, I know this. This is just the divergence theorem. Flux is triple integral of flux density. And so what this gives us then is a nice kind of, you connect the dots inference, which is that you can interpret from this what divergence looks like physically. The divergence of the gravitational field is proportional to mass density. The more dense the mass is in a given area, the more gravitational divergence there will be in that area. So anyway, it's just a nice little bit of physics there. These are equations that you'll see in any physics textbook, any calculus-based physics textbook about gravity. And in various circumstances, sometimes gravitational flux is, for whatever reason, easier to compute, and then you can infer the mass. Sometimes, vice versa, maybe the density is a given in the statement of the question, and for whatever reason you want to know the gravitational divergence. And much easier than dealing directly with density. And, if I have density in a given area, I'm going to have to compute the gravitational field coming out of every particle in that general vicinity. Then I have to add up all of those gravitational fields coming from all those individual particles. And then I've got to compute the divergence of that total gravitational field. It sounds like a nightmare of a question. Right? Much easier to make this argument that we've just done and say, oh, you've told me the density? Okay, well, that's perfect because there's the divergence. It's just a snap. Right? Very deep fact of physics that comes out of being able to make this argument here, which comes out of being able to use the divergence theorem. Right? So this is a point of view on one physical example of why physicists and engineers are super interested in the divergence there. Okay. All right. Electric fields. Very different, I suppose, at least in a physical sense, from gravitational fields. Here's the wonderful thing, though. They're also inverse square radial when you have a point charge. So structurally, then, they look just like gravitational fields. AKA, they look just like light bulbs, point light sources, point gravitational sources, point electric sources, all structurally the same. So again, you can pretend. Now, whether this is physically true or not, I don't know, no comment. I don't really care. It's not even really relevant whether this is physically true, but you can pretend that electric forces are communicated by little teeny tiny little particles, kind of like photons. Kind of like gravitons. And in fact, in the case of electric fields, they actually call them photons. I think that's confusing. But anyway, little particles that communicate electric force. If you pretend that electric fields are communicated that way, all the equations you write down will be correct because electric fields literally behave exactly as if that were true. So as such, total charge is an integral of charge density. Of course it is. That's what density means. I throw in this common factor here just to set things up for the next equation, but mathematically, of course, it's perfectly legal to multiply both sides by the same constant. I do that because that makes this true. And again, this is something you can just write down. Given a certain amount of charge that you have, you can plug that into your vector field, and then from that vector field, compute the flux. Literally, through, let's say, a sphere. Again, that's easiest to work out on a sphere. And that reveals that this is the correct constant to have multiplied by. And then we can write down the divergence theorem. And we can then infer that that must equal to this. And so again, we have a nice relationship between the physical given, namely how densely are the charged particles kind of packed in with each other, whatever that scenario might happen to be, and what is the divergence of the resulting total electric field created by all of those particles distributed. You know, they're not all located at the origin, and so otherwise it would be a very, very difficult thing to compute. Okay, so real quick point. Some of you all may have taken an E&M course previously and may recognize some of these equations. These are two of Maxwell's equations. So what they call Maxwell's equations. This and this are Maxwell's equations. We call them both Maxwell's first equation because they're morally equivalent. They say almost exactly the same thing. They don't look like it. Right? One's about charge, one's about divergence. They seem pretty different, but now let me try to persuade you that these are morally equivalent statements. I'm going to enunciate both of these in a certain key way, right? And tell me if this doesn't sound persuasive. Charge is proportional to flux. Charge density is proportional to flux density. They really say very similar things. One's about totals of charge and flux. One is about densities of charge and flux. These two equations are basically just integrals of each other. So that's why we call them, morally the same equation in the count of Maxwell's equations. These together are one, really, equation. Okay, a little bit of a physics digression, but I do like to point out that it was the divergence theorem that made that relationship possible, right? Why could we unify these two otherwise seemingly very different equations? Well, because of Gauss's divergence theorem. Okay, how are we doing? Is everybody all right? All right, good stuff. Okay. Oh, and real quick, let me just say one of the things. If you've already had your, and again, a lot of y'all are engineers, and you've already had to take a physics 152, probably, I guess, the one with E&M. If you've already taken physics 152, I hope that this might help sort of make a lot of that was, a little bit hocus pocusy in the physics class, maybe make a little bit more sense. For those of you who have not, give me 2 seconds. Those of you who have not yet had a E&M physics course, knowing the divergence theorem, having this perspective on it is going to be dramatically advantageous in understanding that physics. So, make sure to study up on this real hard before you go into your E&M physics class if you haven't already taken it. Yes, sir?
For the one previous one, the one about divergence theorem comes from generation density. The gradient vector dot FG, what is that?
Oh, this says divergence,
yeah.
Right? Del dot is divergence, and FG is the gravitational field. That's this thing right here.
So is that generation density, or is that?
This is what you might call gravitational divergence, but yeah, it is also generation density, because if you think about it, that's what the gravitational field represents. The gravitational field represents the flow of gravitons. Right? And divergence tells you how much that flow is emanating out from wherever you're measuring it. So yeah, absolutely. So that's why I have this over here. So this divergence is morally generation density, which the idea is, well, where does generation come from? It comes from mass, and so that's why it connects to mass density. Yeah. Is that cool?
Yeah.
Great. All right. Okay, so yeah, I hope this will be useful in your future or past E&M courses. Okay, off of physics. Now on to a new accumulation theorem / density theorem / boundary theorem, however you want to say it. I'm going to go more quickly through the development on this one because we've been down this road quite a few times at this point, right? So large-scale structure. We're going to talk about boundary and the related orientation convention. We're going to talk about accumulation. We're going to then talk about the resulting corresponding notion of density. It's the exact same sort of sequence of thoughts. Again, I do this on purpose, not because for any one of these theorems this is the easiest way to prove it. It's not. But I'm motivating all these theorems by the exact analogous arguments because I want y'all to see them all as being, as they are, morally the same theorems. Right? So this is a focus on intuition, not a focus on rigor. Okay. All right, so here we go. Stokes' theorem. We're going to be looking at surfaces in space. Now, we've talked about curves in space, and we made a boundary theorem, fundamental theorem of line integrals. We've talked about solids in space. That gave us Gauss's divergence theorem. Here, we're going to kind of fill in that gap. Instead of a one-dimensional curve or a three-dimensional solid, we're going to talk about a two-dimensional surface in three-dimensional space. Okay, so given a surface, S, I talk about the boundary curve, right? Boundary of S. And again, everything in sight, we're going to need to have orientations because what are we going to do on curves in vector calculus conversations? We expect to be talking about line integrals. Line integrals require an oriented curve. So I've got to figure out now, given an oriented surface, so this is not just a surface, this is an oriented surface. It has a defined direction through it that is intrinsically the positive direction through that surface. How from that dark blue orientation on the surface would I infer an orientation on the boundary curve? And again, what I'm about to show you is arbitrary. Could have gone either way, right? This decision got made a long time ago. It's compatible and consistent with all of the other arbitrary but effectively standard, right, choices on this matter. So yes, it's arbitrary, but it's also highly standard and so therefore not really optional at this point either. And here's the rule, arbitrary rule. The given orientation of the surface, point your thumb in that direction. Key point has to be the thumb of your right hand. It's arbitrary, but it's the standard. Thumb in the direction of that orientation of the surface. That creates what I'm going to call a swirl. On the surface itself. And what I mean by creates a swirl is, well, if you have your thumb pointing that direction, again, thumb of your right hand, critically right hand. Notice that your fingers bending the way they want to bend, known as, funny business. Fingers of your right hand bending the way they want to will point in a direction around that normal vector. Everybody see that swirl? Okay. So that swirl then, if you kind of move close to the surface, that swirl will sideswipe up against your boundary curve in a direction that is one of your two orientation options, and this is what we call the intrinsic. This is the induced orientation on the boundary. So keep in mind, the word boundary is a loaded word in vector calculus. Boundary does not mean just a curve or just a surface. Boundary means an oriented curve in this case. And so boundary of a surface is oriented as per this convention. What do y'all think? Everybody see the rule? Could have been done with the left hand, right? It would have made just as much sense 150 years ago, or however long. But it wasn't. So this is what we're stuck with. Doesn't matter. It is arbitrary, but now that it's a standard, it matters. Everybody good? All right. So that's the first bit of developing what we're going to develop here. Next, we talk about accumulation. Again, we've been down this road a bunch of times. The whole is the sum of the parts. Some things obviously accumulate. Some things obviously don't accumulate. Some things are surprises and feel like they shouldn't, but actually do accumulate. What we're going to be looking at here, the quantity to consider that will lead to a theorem, boundary circulation, which frankly is exactly the same quantity that we were looking at with Green's theorem. So that's worth noting. Right? It's almost like we're revisiting the Green's theorem scenario. looking at boundary circulation as an accumulating quantity. Now, is there a difference? Of course. Here we're looking at surfaces in space. Green's theorem was intrinsically two-dimensional. Right? But you can think of this in its way, you can think of this as being kind of a 3D version of Green's theorem. Okay, so boundary circulation. Claim it's an accumulating quantity. Well, here's the picture. If I were to look at this piece of surface oriented the way that I have indicated here, thumb, fingers, swirl, etc., the boundary would be oriented that way. Right? Looking at the right piece of surface here, again, oriented as indicated there, finger, swirl, etc. That gives me these pieces of oriented boundary. Whoops. All right, so I have I have the blue boundary of the right half. I have the green boundary of the left half. What happens when I add those together? Do I get the boundary of the whole? Well, here's the whole thing. Its boundary would be like this. So what I have to do is look at the whole boundary, look at the parts boundaries, and ask, do they add up? Do they accumulate? Is green plus blue equal to purple? And, well, you're going to be tempted to say no, but as per usual, if we look at this shared edge here, on that shared edge, we see we go across that shared edge twice in opposite directions, just like with Green's theorem. Right? And so those cancel, and with them canceled, now let's look at the green and the blue. Is green plus blue equal to purple? Yeah, they're exactly the same thing. Is everybody with me? Okay, so we have another accumulating quantity. Boundary circulation accumulates over surfaces. All right, and well, that means all the usual same interpretations. That means that even though we measure circulation on the boundary, we shouldn't really think of it as happening on the boundary. It's accumulating over the surface. I think it's really natural and meaningful to think of that boundary circulation as literally a sum. Let me make some better choices here. It's literally a sum of a bunch of little local circulations happening in the interior. So think of circulation, again, as distributed across the surface. Because it behaves exactly, algebraically, it behaves exactly as if it were literally distributed across the surface. So good to think of it that way to develop intuitions for where we're going, for all the same reasons in all the previous theorems that we've discussed. And with that, we can talk about the resulting density. Right? If circulation really is a stuff distributed across the surface, then we can talk about how much of that stuff, circulation, there is per unit size. And of course here we're talking about little pieces of area. And so stuff per unit area is the corresponding notion of density. How we doing? All right, so again, I think it's a really important idea to make sure to realize that the reason we're interested in this concept of circulation density, the whole reason we're interested in the idea of circulation as distributed across the interior is so that we can think about the corresponding notion of density so that we can relate how much circulation there is to how much area there is. So that we can, you can probably see where this is going. We're going to do a double integral over the surface to add up and get the whole. Okay. All right, so now again, I'm going to skip the details, right? We've got this thing called circulation density, abstract concept that I've defined here, and how to compute it. It turns out that this is the formula for it. Again, don't worry about those details. We can write stuff down. I mean, this is a little bit weirder of a calculation, but it remains, it's just details. The concept is what I think is the most important thing in a class like Math 219. So just make sure to know that this right here is the formula for circulation density. And don't worry about why this is the formula for circulation density. Is all willing to buy that? Okay. All right. Now there is an oddity I need to point out. If you look back at Green's operator, what you'll find is that it depends only on the vector field. dq dx minus dp dy. Full stop. It only depends on the vector field, p, q. That's it. If you look back at the formula for divergence, right, flux density, it only depends on the vector field, right? It's the partials of p, q, and r with respect to x, y, and z. That you can compute it only knowing the vector field. Sadly, weirdly, disturbingly, not so for circulation density in space. It depends on the vector field, but it also depends on the surface. It depends on, I need to know that normal vector to the surface, describing how my piece of surface is sitting in space, right? That normal vector, weirdly, is part of the formula for circulation density. It's an eyebrow raiser. It's not like Green's operator in that sense. It's not like divergence in that sense. So this is uncomfortable. Does everybody see why I'm sort of concerned about this? A little bit worrisome. But it's going to turn out that this actually does make good sense, and we're going to draw some pictures and make sense out of this, to some degree. In fact, we have seen something like this before. And I'm deliberately sweeping under the rug for the moment. But I'm going to admit to what I'm currently ignoring in a couple of pages. Okay, so anyway, I just wanted to sort of point that out, and we'll make sense out of that later. For the moment, we've got circulation density. We've got a formula. Let's put it all together, make a theorem, and solve a problem, get one into the win column. And then we'll come back and make sense out of it later. So here we go. Circulation is a quantity that accumulates. The whole is the sum of the parts. And I can compute the differential amount. Oh, you know what? Bad color choice. I can compute the differential amount of some piece of circulation by relating it to circulation density, asserted on the previous page. Right, stuff equals stuff per unit area times area. And check it out, we've got ourselves a theorem. If you want to compute a vector line integral, you can do so with a vector surface integral of the curl of your original vector field through the surface whose boundary is your original curve. And now I'm going to do the rewrite here now that we've got a result. Recall that this right here, in a stroke of seemingly just completely random good luck, we've got little n times ds scalar. That was our definition of the ds vector. And so I think it's better really to write down this theorem like this, because then, well, for one thing, this is just a more compact, more convenient, more natural notation. But look at now, my integrand only depends on my vector field now. The dependence on the surface is now completely wrapped up in the vector surface differential. Everything that doesn't have to do with the surface is outside of the differential. How are we doing? Did I see a hand at some point? Yeah.
Is the n unit normal or just?
Yeah. This is the orientation unit normal. That's right. Yeah. It's got to be a unit vector, and specifically it's got to be the normal unit vector that's defining what is the positive direction through the surface. Right. Is that satisfying?
Yeah.
Okay. Right. Anybody else? Let's see an example. It's weird. I like to point out it's weird that how this comes up. We thought we were making some argument about how we have an accumulating quantity and there's an associated density. What we've ended up with is a tool for computing line integrals. Circulations specifically, in other words, line integrals around closed curves that are specifically boundaries of surfaces. If you want to compute a vector line integral around a boundary, you have an alternative here. You can compute a flux instead. And that can be a really convenient, powerful computational tool. For example, here we go. Here's a question. Notice it says we want to compute the line integral. Notice that we've got a vector field given. Notice that we have a curve given. Let me hit that better. Anyway. So, vector field given, curve given, compute the line integral. Now, in fact, notice even more so, not only is the curve given, but the curve comes pre-parameterized, right? We've got a parameterization given. This could be viewed as kind of nudging you towards, hey, here's the parameterization. You could compute the vector field with a parameterization. I'm giving you the parameters. It's almost encouraging you to pull back through the parameterization. Yeah. I just want to warn y'all, don't fall for it, right? And assume that just because the curve is communicated in a particular way, that means that that's the best way to solve the problem. Life doesn't work like that, right? There's all sorts of circumstances where a curve will come to you parameterized, but you need a different take on the curve. Or a curve may come to you in some other form, but you need to parameterize it, right? So don't just take questions at face value. You have to interpret and decide for yourself what the best solution is for solving the problem. Okay, so what we're going to do here is we're going to look at this curve. Okay, that makes me feel better. We're going to look at this curve and ask ourselves, what is the best take on this curve? Yeah, it's parameterized. That's nice. Okay, what else do we know? Well, that curve as a circle, right? X squared plus y squared is a constant and z is 0, so this is a circle, right? And you can observe furthermore that this is in fact just a reflection of our sort of basic standard circle in the XY, unit circle in the XY plane. Right? So we know exactly what our circle looks like, and being as it is a reflection of the usual, we know that its orientation is going to be kind of, the opposite of the usual. It's literally flipped over from the usual. So this is what you might call clockwise as seen from above. How are we doing? Is everybody on board? Okay. All right. So what does this tell us? What can I say about this curve here? This curve that is a circle in the plane oriented in a certain direction. And the key idea is to observe that this is a boundary. Okay, this is the boundary of that surface there, S. But I do have to think carefully about orientations. Remember that word boundary is a loaded word. You've got to respect orientations. Orientations matter. I know it's just a minus sign, right? But it's it's a minus sign that's connected to a deep idea, and if you want to get right answers, which we do, then that minus sign is representative of an understanding of a deep idea. So this is a very important minus sign. The correct interpretation of orientation on the surface on a exam, if this were an exam question, let's say worth 20 points or something, getting the orientation right would be worth several points. So just heads up. Don't say I didn't warn you. I don't want to tie myself down. Everything depends on the particulars of a given question, but I wouldn't be shocked if it was 4 points. something like that. So very, very worth paying careful attention to. This is one of the big ideas with Stokes' theorem, is proper interpretations of boundary orientations. Okay, so we've got given, it's implicit in the parameterization here, we have an orientation on the boundary curve. I've kind of reverse engineered that this is the boundary of a given surface, namely this disk. Which orientation on the disk? And the way you answer this question is basically trial and error. We know how to take a surface orientation and infer the boundary curve's orientation. We're trying to work backwards. We're trying to take the boundary orientation and reverse interpret the surface orientation. So just try both of the options and see which one works. So here we go. Let's try what's going to work out to be the wrong answer. First, let's suppose that my orientation were like this. If that were my normal vector, if that were my normal vector, then thumb and fingers and swirl would have me swirling around that way, which would give me the wrong orientation on the boundary. So that we tried and failed, right? That shot in the dark first attempt to, speculate on what the orientation is on S was just wrong. Hey, no harm. We realize it's wrong, so let's see here. Let me get that out of here. There we go. Now we consider the other option. Now, a case could be made, by the way, process of elimination. We know this has got to work because there's only two options. We know one of them's right. We know the other one's wrong. We know the answer, but let's just think it through. If I had a downward surface orientation, then look at my right hand, right? Fingers of my right hand. See how they go around the other direction now. Which gives me this induced boundary orientation, which is correct. Everybody see how that worked? You just try them both, see which one works. One of them works, one of them doesn't. And it's just trial and error. Okay. So that's why this is our normal vector. 0, 0, -1. Again, getting it wrong. If you were to put 0, 0, 1, it's going to be a big problem scoring wise because this is a sophisticated concept intimately connected to the use of the theorem. So make sure to think that through carefully. Okay, so it's all over but the shouting at this point. We just have to kind of write things down. We have realized, let's see here, let me get back into the right mode here. We've realized that our curve is a boundary. Stokes' theorem, again, the catch on Stokes' theorem is that it allows you to compute line integrals only if that is a line integral around a boundary. Just like with Green's theorem, that's equivalent catch. And so, Stokes' theorem then leaves us with this surface integral. Apparently, we're going to need to compute the curl. Reminder, computing curl. Oh, no, let's see here, color choices. Computing the curl is a bunch of partial derivatives. And make sure that you're proficient. Make sure that you can crank that out nice and quick. Right, you want to make sure that you can just instantly write down the formula, that you can instantly compute the appropriate partials. Be really careful not to get those terms backwards. Remember those minus signs in the formula for curl. Make sure you get that right. Right, these little details really matter a lot. So anyway, as it turns out, here's the curl. Worked out really nicely. Much more desirable as an integrand. Right? We've already agreed that our orientation unit normal for our reverse engineered surface, anti-boundary surface, you might say, is 0, 0, -1. And it's all over but the shouting. This is an easy dot product. We have a surface integral of a constant over a garden variety surface, and answer. What do you think? Everybody all right? Okay. Really nice tool for the toolbox. We have yet another tool now for computing line integrals, specifically line integrals in space. If the line integral is a boundary line integral, which again, notice now in the statement of the question, notice nowhere in the statement of the question did it say, hey, by the way, this curve's a boundary, or use Stokes' theorem to compute the line integral. No, there was no hints in the statement of the question. Again, this is how life comes at you, right? Problems come up without the solution subtexted. So, you have to analyze the question, think about what your options are, and then from that, decide what computational tool you're going to use. Okay. All right. So, let's get back to that whole business about the normal vector showing up in our circulation density formula. Here's where we've seen something like that before. And again, I deliberately swept this under the rug at the time. I didn't want to get we had enough going on as it was. We had accumulations and formulas and worrying about orientations, and there was a lot to deal with. So with that all established, what's the deal with having an orientation in the formula for the density? Here's where we've seen it before. Fundamental theorem of line integrals. And our formula for change density was this. Right? So, we've seen it before. So, what I did at the time is I said, well, look, you can kind of lump all of this together, call that the dx vector, which we've done before, which is natural, which we like, right? And thinking then not in terms of size, but thinking of dx as, well, it represents both size and orientation. So I like to call this oriented size, if you will. Right? It's a displacement vector. It's the displacement differential. Yeah. But let's think of this as oriented size. Play along, If you think of this as oriented size, then it stands to reason that this thing maybe should be called an oriented density. That's just one way to think about it. Right? And let me flesh that out a little bit more. I'm going to rewrite. Let's see here. Let me rewrite this whole thing here. I'm going to rewrite the gradient of f as magnitude of the gradient times the direction of the gradient. There's my gradient vector. And then, of course, we've got dot t ds. Right? This is what we've got in the orange. This is what makes up our little pieces of change, if you will. This is our d delta. So, how do we group these together? What should we call what? If you insist on focusing on thinking of ds and only ds as being the size, well, then you kind of have to do this weird thing of lumping all of this together as if those are all part of the same thing, and that's your integrand here, and that's your change density, and you can do that, right? But it really just makes more sense, I think, to lump in a more natural way. Let the curve's orientation be a part of what you're using to describe the curve, namely dx, right? And that leaves the gradient as your integrand. And that also leaves that there's really two things about the gradient that matter. The magnitude of the gradient matters, and the direction of the gradient matters. Of course it does. Right? Think back to chapter 2. We know that the direction of the gradient is a big deal. That's very naturally part of what the gradient is. It's playing a role, right? It's telling you what the direction of fastest increase is, what direction you have to go to realize this, what you might call steepness or whatever you want to call it in that direction. So it's really much more natural to kind of separate the vectors in the dot product. It's just makes more sense. So likewise with Stokes. Right, here's Stokes' theorem. And again, you can kind of lump in the normal vector as part of the integrand, I think that's sort of unnatural and weird. It really makes more sense to think of this as being your oriented area, if you will. Right? And then along those same lines, what we end up with is an oriented density. Again, don't forget, circulation is our quantity at hand here. We're computing circulation, and so this is oriented circulation density. So this is how I want you to think about curl. Curl is oriented circulation density. It's telling you, in some sense, how much is my fluid rotating in the same way that Green's operator did. How much the fluid is circulating, and it also tells you what is the direction, what is the axis around which that circulation is happening. And you can see that in this picture right here. Curl pointing like this tells you that the fluid, the rotational aspect of the fluid, whatever it is, and again I have it here a pretty generic example of a fluid literally going around in circles. Not that it always does that, right? But if there is a circulation, that circulation's got to be naturally around a certain axis. The curl points in the direction of the axis that rotation is around. And we got to draw a line right here. We'll pick up here on Wednesday. Y'all have a good rest of your Monday. See you later. Don't forget to stick around for a 10